Okay, so my name is Aryan, not that one. And you all have must seen all those huge equations like general this equation, general that equation, general heat conduction equation, which we have derived in previous video. But have you wondered like what the hell does this huge equation really does? What is the reason we are studying this? So today we'll be seeing one of those user cases of how this equation works and all that stuff. So let's start. Okay, so let's say there's this one wall of distance L, right? So thickness L, and there's temperature 1 at this side. It's higher temperature. There's temperature 2 at the right side of the wall, and temperature flows like this. Now, to get the diagram, or let's say if we go and ask the wall, hey wall, tell me this. At distance is equals to x, what your temperature is. What do you think? Wall is going to answer this? How are you going to calculate temperature at this point? Let's say it's X from the start. So for that, and someone might just comment it saying, use thermometer, mate. Now gonna put a thermometer at every part, right? So yeah. So to calculate the temperature Tx, which is temperature at distance x on this wall, we can use the general heat conduction equation, which is pretty much del square T plus Q dot generation upon K is equals to uh, 1 upon alpha into dou T temperature upon dou tau. Right. This was a general equation, right? Now, first thing, this del term is basically dou square upon dou x square plus dou square upon dou y square plus dou square upon dou z square, which pretty much tells us the change of any quantity in the three different directions x, y, z, and all. So that's very important. Another Q dot generation term is basically if wall is producing heat of its own. But the thing is, this general heat conduction equation, it looks really huge, right? And when you look at a huge equation, you realize that we can't really solve those huge equations, right? Like we get the feeling that we can't really solve the huge equations. Well, my friend, that's true. Yeah, that equation is really huge, and like I'm not some sort of like genius or something that I can just look at the equation and solve it. So what we do usually is we uh, use assumptions. We put different assumptions to eliminate as many terms as we can. Like for example, in this case, in the case of wall, I'll write assumptions right here. Assumptions. It became as anyways. Assumptions. The first assumption is that heat transfers only in x direction. Only x direction. Second assumption is gonna be no internal heat is being generated. Internal heat, right? Third assumption is gonna be, so let me tell you why I took all these assumptions. Okay, first I'll tell you all the assumptions and then I'll tell you that. Right. So third assumption is gonna be k is constant in all directions, which is basically k x is equals to ky is equals to kz is equals to k. And fourth assumption is gonna be it's in steady state. Steady state heat conduction. Okay, now let me tell you why we took all these assumptions. Because also let me expand this equation. So you realize what happened here. Dou square t upon dou x square plus dou square t upon dou y square plus dou square t upon dou z square plus q dot g upon k is equals to 1 upon alpha dou t upon dou tau. This huge equation, we will have to solve this huge equation just to get all the answers uh, in this case. But when we apply these all the assumptions, like these four assumptions, the first is changes only in x direction. Changes only in x direction. That means we eliminate the y term. Let me change the color. That means we eliminate the y term is equals to 0. Also, x is only in, sorry, heat is only in x direction. That also means we eliminate the z term because change in z is also 0 because there's no change. Now, no internal heat is being generated. So, this internal heat generation term becomes 0 and it's in steady state. So, if it's in steady state, then there is no change in temperature with respect to time as well, right? This also becomes 0. So, are you able to see the same thing that I'm seeing right now? We eliminated almost everything except what we need. So the equation becomes dou square t upon dou x square is equals to 0. Like, you realize that the huge equation went from this to this. Also, k, we took this assumption that kx is equals to ky is equals to kz is equals to k, which made k constant. So due to that, we were able to write it in this equation, or else it would have been even a bigger equation. Like, let me show, or like there will be different k terms like kx, ky, kz in all these equations. So equation would have been even more bigger, right? So what you see what we did here, we just reduced the whole equation. Like, we just made it so small. Now this is very easy to solve. Like, it's just differentiation. So now what we can do is just take this term dx into or no, wait. Now what we have to do is just integrate this equation. When we integrate it once, we'll get dou t upon dou x is equals to c1. C1 is a constant. We don't know what this constant is yet. And then uh, what we'll do is we'll take this x term in the right direction, right hand side with the c, and then integrate again. Integrate again. Then what we'll get is dou t is gonna be just t, not dou t. You know what? Let me write this new equation as well. Like, dou t is equals to c1 dou x. Now after integrating this, we'll get t is equals to c1 x plus c2. C2 is new constant. This is the new equation that we got. Let me make. Hmm, Man, why can't a line be straight? Why does it always have to not be straight? If you know, you know. Okay. Yeah. So this is the new equation that we got. Right now, what we have to do is this equation tells us the value of temperature with respect to distance, which is t, change of t with respect to x. But yeah, we don't know the value of c1 and c2. Those are two constants. So what we have to do here is just apply boundary conditions. Like, let me write boundary conditions right here. Let me show you. This is this point. This is the wall. This is the start. This is the end of the wall. And what did I just write there? Yeah, this is the end of the wall. E and D. All right. So at the start of the wall, x is equals to 0, and your temperature T is gonna be T1. At the end of the wall, x is going to be equals to total distance of wall, which is L. So temperature is gonna be T2. Right. Just put these two conditions, two different boundary conditions. This is condition 1, this is condition 2 in the equation. And what we'll get is, let me write it in different color again. It's going to be a bit more easier to understand. Yes. Boundary con, con condition 1. Boundary condition 1. Applying boundary condition 1. Apply boundary condition 1. The new equation becomes at x is equals to 0. T is equals to, so this was condition 1 and this was condition 2. So at x is equals to 0, t is equals to t1. So t1 is equals to x is 0, so c1 is 0, c2. So from here we get the value of c2. Now let's put the condition 2. uh, I mean, let's put the value of C2. There's a C2 in equation in this equation. Putting value of C2 in this equation, we'll get T is equals to C1 x plus T1. This is the new equation that we got. Now, let's apply the boundary condition to this equation, boundary condition second to this equation to find the value of C1, which is at x is equals to L, T is equals to T2. So the new equation becomes, uh, let me write it here. Condition 2. So the new equation becomes T becomes T2. T2 is equals to C1. It stays constant. We are finding the value of C1. C1 into what is the value of x? X is going to be L C1 L plus T1. This is the new equation. Now from this equation, we can just like find the value of C1, which is C1 is equals to C1 is equals to T2 minus T1 upon L. This is pretty much it. Now we have the value of C1, we have the value of C2. We can just put it in the equation and we'll find the change in temperature. I will write it in hashtags. Put values of C1 and C2 in equation. Let's name this one equation 1. So the new value of temperature becomes T is equals to what is C1? C1 is basically T2 minus T1 upon L into X plus what is T2? It's pretty much T1, right? Now, this is pretty much the final equation that we are gonna need. Like we can just change the positioning of all the terms and all in however way we want, but this is pretty much it. Like if we put the value of T2, which is temperature at the end of the wall, minus T1, which is temperature at the start, upon length, into whatever length we want, like whatever distance from the start we want, the temperature of the distance from the start we want, plus again T1, we'll get the value of T. And yeah, that's pretty much it. Like this is how we can use general equations, and this is applicable in all the equations, like not just this one. Mm, there are so many equations, Navier-Stokes and all of those. Like this methodology is applicable in all the general equations. Like just whatever you want, just find whatever you want by eliminating all the unnecessary terms, by making some very specific condition, and you'll get a final equation, something like this. Yeah, that's it. That's what the general heat conduction equation wants you to know. Thank you.